Hey there, welcome to a video discussing pages 5 and 6 of the section 4.3 notes. Here we're going to talk about derivatives of inverse functions in general. So let's look at the results we obtained from derivatives of our inverse trig functions before we rewrote our results to the terms of x. So remember we had oh, Miss Dallas is not working. I don't know how that happened because I haven't used it. Yeah, give me one sec here. Just gotta use my mouse. Adjust the volume here a little bit. Okay. Anyway, yeah, so y equals inverse sine of x, right? When we did that, we got that as our derivative. Now, and then of course we got in terms of x, but before we worry about that, remember when y equals inverse sine of x, that's the same thing as saying x equals sine y. Now so this is the inverse, right? The original obviously was y equals sine x. If I take that derivative, I get cos x. But the inverse, again, that's when you switch x and y, and then when you isolate y, which is over here, that derivative is 1 over cosine y. So it's interesting that the derivative of the original, so if my original is y equals sine x, and that derivative, of course, is cos x, and then when I do the inverse, which is x equals sine y, and of course you isolate y, so y equals inverse sine of x, that derivative was 1 over cosine y. So it looks like they're reciprocals in a way, the derivative of the original and the derivative of the inverse. Or let's look at tangent, right? So y equals inverse tan of x is the same thing as saying x equals tan y, and that our derivative is that. If I had the original function y equals tan x, my derivative there is going to be secant squared x. So it looks like those are also reciprocals too. So we notice that the derivative of the original function equals the reciprocal of the derivative of the inverse function. But x and y, what's the right word to use? But replace x with y, or vice versa. So that's what we're kind of noticing here. And this is true for all functions with inverse functions. So in a way we can actually differentiate this. F of y equals x. That's the same thing. If y equals inverse f inverse of x, then f of y equals x. If I actually do implicit differentiation, you have f prime of y equals dy over dx equals 1. So dy over dx is 1 over f prime of y. Where, of course, if y equals f of x, then dy over dx will be f prime of x. And because both these equal dy over dx, we could safely say that f prime of x equals 1 over f prime of y. And actually, it's in our cheat sheet too. Let me open up the cheat sheet really quickly here. That's at the bottom right here, right? F prime of x equals 1 over the inverse, the derivative of the inverse of y. So, and actually, f of y, just so you know, is going to be the inverse, because you're swapping the inputs and outputs. Some other things that we need to mention here too. Remember that when we have the graph of y equals fx, the graph of the inverse will be a reflection about y equals fx in the line y equals x. So you might remember this back in the day, like when you had, say, y equals x squared. You switch x and y. So y is plus or minus root x. So your inverse would be this. And remember, our original was this. So here's the original. Here's the inverse. And a reflection about y equals x. That's always going to be true between the inverse and the original. Now, let's take a look at these two graphs down here. You have f of x and inverse of x. Point T is on the original. Point R is on the inverse. And R is going to be, is going to have the x, y values switched, because that's what you would expect when you reflect about y equals x. So we draw these two small right triangles where the hypotenuse for each one is going to be a tangent line. And we see that the slope here is P over A. We see the slope here, sorry, P over Q, that's what I would say. The slope here is Q over P. So again, the slope of line R is P over Q. The slope of T is Q over P. Sorry, that was really messy. I could draw better than that. So what happens is that the slope of a tangent, we know, is a derivative. So when you have inverse, we have original function and inverse function, their slopes are going to be reciprocals of each other. And each derivative is valued at its particular x value. So obviously, this is going to be f inverse b, because you're at x equals b here. And this is a derivative of f at a, because you have a is your x value there. So essentially, f prime of a will be 1 over f negative 1b derivative. Because remember, that was q over p, and that's 1 over p over q, which flips over to q over p. So let's keep moving here. This might be help having this pictorial diagram. And we're going to spend a lot of time talking about this when we meet again on Thursday. So let's say your original function has c comma d. And again, let's take a look at a very another type of function. Let's say y equals 2x plus 1. So f of x equals 2x plus 1. So I replace f of x with y. But then to do the inverse, you have to swap these, x and y, and then you have to isolate y. So y is x minus 1 over 2. So that's going to be your inverse now, x minus 1 over 2. So for my original, let's say I plugged in 2. Well, f of 2, of course, is 5. Then guess what? For my inverse of 5 will equal 2. So they should, right? We know this. So if you have c comma d for the original, then you have d comma c for the inverse. So whatever f prime of c is, so f prime here is going to be f prime of 2, actually. It's just going to be 2. Derivatives, it's very simple, just 2 here. My derivative here is going to be 1/2. Even if I plug in 5, it doesn't really matter, because you get 1/2 anyway for your derivative. And those are going to be reciprocals of each other. So we can actually use this methodology for example 6. So you're told that these are differential functions. That's important to know on real numbers. f5 equals negative 11, and the inverse of negative 11 equals negative 3. So to derive the inverse at negative 11 equals negative 3. Well, if f5 equals negative 11, so you can kind of use this little schematic here, right? If you have 5 comma negative 11, then you have negative 11 comma 5. So what this means that f prime of 5 will equal the reciprocal of the inverse derivative at -11. So the derivative, so first of all, this is just going to be 5 because you just swap these as we did over here. Then f prime 5 is going to equal 1 over the inverse derivative at -11, which will be -1/3. Let's look at this just a bit more. We can wrap up the video. So for derivative inverse functions, again, the assumption is that f is differential at every point on the interval, and dy over dx will never equal 0, because if it does equal 0 and you're doing a reciprocal, then you're gonna have a problem, right? So you can't have to assume that your derivative won't equal 0. Then f will have an inverse as well, and it'll be differential at every point on the interval that we had for the original function. So the assumption is that you're not gonna have discontinuities, not gonna have sharp corners, vertical tangents, and so forth. And also one-to-one, meaning it passes horizontal line tests, sorry, vertical line test and horizontal line test. Why we care about that is that if your original function fails a horizontal line test, then your inverse would fail the vertical line test and would no longer be a function. That's kind of why we care about that too. But and also, if you did have something like this here, then you have derivative 0. Then you would have a derivative that's undefined on the original. That's another problem too. Whenever a graph does something kind of like this and fails the horizontal line test, you are going to have a peak somewhere, meaning you have a 0 derivative for the original, but then we do the reciprocal to get the derivative of the inverse, it's going to be undefined, right? So I'll talk more about that with you guys on Thursday to emphasize that a bit more, but you do have to make sure you pass both vertical and horizontal line tests, because again, if you fail the horizontal line test for the original, you are going to have a horizontal tangent. Derivative is going to be 0 in the original, and we do the reciprocal, that would be 1 over 0. That's a problem. Anyway, let's look at example 7. Show that f has a differential inverse. Okay, well that's not so bad. Just take the derivative, right? I mean, take the derivative. That's just going to be 8x squared plus 5. So definitely we have a derivative that seems okay. We don't have any problems there. This will never equal 0 because 8x squared can't be negative and you're adding 5. Also the fact that this is a nice smooth curve, right? 2x squared plus 5x. If you were to graph that in Desmos, I think there's an x-intercept of 0. And I think an x-intercept of I think that was it, just an x-intercept of 0. So it kind of looks like this. And that is 1-to-1. It passes both vertical and horizontal line tests. So vertical line test fine, horizontal line test fine. So that's how you kind of show it, is do a graph and take the derivative. Look at graph. Make sure it's 1-to-1, meaning passes vertical and horizontal line tests. Remember that from pre-cal. And then differential invert, and then also just make sure f prime does not equal 0. Therefore, when you do the reciprocal, you'll be okay when you find the derivative of the inverse. So that's how you do part A. For part B, I'll do that in red. F of 2, that's super easy. That's just 2 times 2 cubed plus 5 times 2. See, it's 16 plus 10, that's 26. Easy peasy, right? So f prime of 2, well, f prime of x, that's easy also. That's just going to be 6x squared plus 5. So f prime of 2 is 29. Great. And I'll do this in blue. Now, to find the inverse, you could actually, if you want, right now y equals 2x squared plus 2x cubed plus 5x. So you could switch x and y. The problem is that isolating y is going to be impossible here. So instead of doing all that, that's not really wise. Then you just realize that, hey, you know, let's use that little trick we just did with the box. We have 2, 26. Then you have 26, 2 for the inverse, right? Switch x and y. So that's easy. That's just going to be 2 here. Because remember, the whole point of an inverse is switch x and y. So if f of 2 is 26, then inverse 26 is 2. And then remember, f prime of 2, the derivative of the inverse, sorry, the derivative of the original will be the reciprocal of the derivative of the inverse. But you have to, you know, plug 26 in as your input. So that's just going to be reciprocal of 1 over f prime of 2, which of course is 1 over 29. And we have that worked out. So you have a couple of problems in the textbook to try this out. If you get stuck, that's okay. It's kind of a weird concept. I'll do another more drawn out example with you guys in class. And we have some worksheets we'll work on as well so that you guys feel more comfortable with this concept. And that's the end of the video.